Thank you for coming. Our CVPR subject paper, Multi-Modal Learning with Modality via shared specific feature modeling. My name is Juan, and this is our author team from the University of Adelaide, and this is our paper tag. I prepared a quick look for the paper. So this is our framework. We have multiple features with different specific encoders. And we have one shared encoders to give the specific feature and shared features respectively. And the shared features and specific features will be fused for those available modalities. But for missing modalities, they will be generated from shared features. So we propose the shared specific model that is significantly simpler and effective and can adapt it to multiple tasks easily. And this is a quick look of the results. So on brass data set, the shared specific improved the SOTA by more than 3% for ET, 5% for TC, and 3% for WT. I'll give a detailed introduction about the paper later. Thank you. Our main contributions. So we propose an extremely simple but effective multimodal learning with missing modality method called shared specific feature modeling shared spec, which is based on modeling and fuse shared specific features to deal with missing modalities in both training and evaluation, and also it can be used for dedicated and non-dedicated training. And the second, to the best of my knowledge, our proposed model is a first missing modality model that can be easily adapted to multiple tasks, including classification and segmentation. And last but not least, from the experimental point of view, our results on CV classification and medical image segmentation benchmarks show that our model can achieve SOTA performance. And more specifically speaking, on breast 2018 dataset, our model can improve the segmentation accuracy by more than 3% for ET, 5% for TC, and 3% for WT. So here's the structure of our model with full modalities. So we have multiple modalities from X1 to X_N, a path through one shared encoder to get shared features, and several specific encoders for each of the modalities to get specific features, and represented by R and S respectively. And in a residual learning manner, as shown here, the shared features and specific features are fused together and funneling with their linear projection to give the fused features in the end. So the dashed blue arrows indicate different objective functions. So we have a domain classification objective to constrain the specific features only care about the information for those modality specific features. And we have distribution alignment objective to constrain those shared features for each modalities to be close to each other. So this is the structure of our shared specific model with missing modalities. Without losing generality, we assume X_n is the missing modality. So for those available modalities, we actually have the exactly same procedure as what we have in the previous slide with full modalities. So the only difference is with the missing modality X_n because of the missing. So the final fused feature F_n is not available. Actually, it's generated from the available shared features. So the gist behind it is, even without the modality specific features, but the shared features can already capture the shared informations, already be good enough for the final prediction. And we also have the dashed blue arrows indicating different object functions, the distribution alignment objectives, and the domain classification objective will be discussed in detail later. Now let's talk about two different types of objective functions in detail. So we firstly look at the domain classification objective, which is for specific feature learning. So inspired by domain adaptation technique, we propose to adopt a domain classification objective, which is short for DOC, for the specific feature learning. The intuition is that if the specific feature for a certain modality can be used for this domain classification, so basically it can be considered valuable information has been contained in these specific features. So for this domain classification, cross entropy loss is being adopted as what we have for the equation 5 in the paper. Next, we're going to look at the distribution alignment objective for shared feature learning. So for shared features, we want them aligned with each other. And different with the previous slide, for this objective function, we actually develop three different types of variants. So the first one is achieved by the negative of CE laws as what we have in the previous slide. So basically, we add a negative sign in the beginning, trying to confuse the domain classifier. Another option for the distribution alignment objective is to minimize the KL divergence between probabilities produced by the shared feature representations. So to reduce the computation complexity, we project the features onto low dimension space through a linear projection, as what we have of the equation 7 in the paper. Another one option for a DAO is pairwise feature similarity using the p-norm. For example, like L1 distance, L2 distance, etc. From the experimental results point of view, we apply our model on medical image segmentation dataset and the computer vision classification dataset. So for a medical image, we applied it on RAS 2018. Here is a basic information of RAS 2018. It consists of 3 types of labels, and with 285 cases for training and validation together, 16.6 cases for testing, and is online evaluation. On the right are 2 tables. We tried it on following existing works. We tried it on non-dedicated and dedicated training. So for the above is non-dedicated training, and the below one is the dedicated training. So for non-dedicated training, basically we train our model once and test on different individual mixed modality situations. But for dedicated training, we train each model for different types of mixed modality situations. So you can see, no matter in non-dedicated or in dedicated training, our model can surpass the current SOTA model by a large margin. From the analysis and visualization point of view, as mentioned in the above slides, the distribution alignment objective functions actually have different type of variants. So we test our model on different types of object functions, which is cross entropy, KL divergence, L1 loss, and MSE. So in the table as shown here, best for each of the role, the best model is represented by a red color, and the second best is in blue. And you can see the L1 distance basically have the best performance in average. On the right, which is the testing visualization, the shared specific features of 4 modalities in breadths. So the shared features of 4 modalities are represented in X, here overlapped with each other really well. And the specific features of 4 modalities are represented by O in different colors. You can see they have strong boundaries, which is have clear boundaries with each other. So basically have a corresponding like with our expectations. That's my presentation. Thank you.